So now what can we do to maybe reduce the cost of that a little bit? Because we know making all these arc magnets, there's more processing cost to that. And the most cost-effective shape, the most cost-effective topology for a magnet is going to be a rectangle. So just a simple rectangle magnet. So looking at this slide, you can see that between my wedge shape pole pieces, I now changed those tangential magnets to a simple rectangle shape. So a flat-sided magnet's, again, easier to manufacture. And if the tangential magnets are changed to have flat sides, then only the pole magnets will need angled machining, as you see in this picture here, and indicated with the little 90-degree mark. Okay, now we're going to look at the resultants of inserting the rectangle tangential magnets into that topology. So looking at the graph on the right, we can see that the blue torque curve is all the wedge shape configuration, and the green is the rectangular tangential magnets. So we can see that those lines are really both right on top of each other. So we reduced the manufacturing cost of the rotor slightly by reducing the complexity of the magnets, and we're still getting consistent performance out of that system. Now let's see if we can take that a step further on this slide. Can I actually use a weaker magnet for my tangential magnets and just leave my very strong magnet for my radial magnets? And we want to take a look at this because the stronger a magnet is, a little bit more expensive that magnet is. So can we use a little bit weaker magnet, a little bit more cost-effective magnet for those tangential pieces? So for this example, we used a Ricoma 30 MGOE, samarium cobalt magnet for the tangential pieces, and we stuck with the Ricoma 35E, like we have in the previous cases, for those radial pole piece magnets. We left the tangential magnets as rectangles, and we left the pole pieces as the wedges. So now we're going to plot that torque curve on top of the previous two cases. And when we look at that torque curve, we can see that the blue line, again, is the all-wedge configuration with all the same strength magnet, the Ricoma 35E. The green line is the rectangular tangential magnets, still all the same material, but now we've added on this dark blue line. So the dark blue line has rectangular R30 MGOE tangential magnets. So looking at this though, if you look at not just the top curve, which is the torque, but if we look down at the torque ripple, you can see that the torque ripple is actually reduced when we inserted those slightly weaker magnets for the tangential pieces of the Halbach array system. So really good effect overall. Again, the SPM and SPP, the width of the pole piece and the pole pitch did change slightly because we did weaken that magnet. But overall, we see a really good resultant, and we just reduced the system cost two ways. Again, the tangential magnet being a rectangle, and also using a slightly weaker material, more cost-effective material for those tangential magnets. Now, what can we do to maybe take one more step? So in this last step, we're going to now take our pole pieces, the Ricoma 35E pieces, the strong ones, and since that is a higher grade material, more expensive raw base material, let's try to also make that one the cheaper configuration in terms of the shape of the magnets. We'll make that one the rectangle, and we'll make the tangential magnets, we'll make those ones the arc pieces. Again, because we still want to have a complete fill around the circumference of the rotor with magnet material. Air is not going to help us at all. So we want 100% magnet material between the magnet carrying rotor and then the outside looking at the air gap between the rotor and the stator. So the pole magnets can also be changed to have the parallel sides. So if the tangential magnets are changed to Ricoma 30, it reduces that cost. So now we'll take a look at the results like we have in our previous study. So again, same graph, we're plotting the torque ripple. And for the cases, now you can see everything plotted on top of each other. So the blue line, again, is all wedge R35E. The green is the rectangular tangential magnets, which is, again, all Ricoma 35E. The dark blue is when we switched out those tangential magnets with a 30 MGOE material in the wedge 35E poles. And our newest case is going to be the orange dots, which are a rectangle 35E pole piece And then now the wedge shapes, my tangential magnets, are the 30E. So you can see we've done a lot with this system. We're still getting the same performance out of the system overall, but we've made the magnets a little bit more cost effective. We've made them a little bit easier to manufacture, and we're still getting that same overall performance. And we've actually lowered, that torque ripple a little bit with this different configuration. So in terms of power density and manufacturability, some really good food for thought when you're working on your surface mount permanent magnet motors in the future and you want more power density and you want to use a Halbach array configuration.